Forecasting energy consumption in the Chimborazo province, Ecuador, using random forest and XGBoost algorithm. Introduction. This study focuses on forecasting electrical energy consumption in the province of Chimborazo, Ecuador. Data from January 2015 to April 2023 is used for the training and evaluation of machine learning techniques. The study focuses on residential, commercial, industrial, and auto clients, characterizing electricity consumption by cantons and parishes. Forest. Random forest is a prediction model that combines multiple regression trees trained on random data samples to make more robust and accurate predictions. XGBoost, extreme gradient boosting, is a machine learning technique known for its high accuracy and effectiveness with structured data. It uses the gradient boosting technique to create a powerful ensemble model. Evaluation of model accuracy. For the evaluation, the metrics have been used: coefficient of determination, the root mean square error, RMSE, and the mean absolute percentage error, MAPE. Comparison methods. Database collection. Monthly reports from regulated clients are used that detail quantitative aspects of consumption in the province, cantons, and parishes in the residential, commercial, industrial, and other sectors. The reports are available on the Ecuadorian Electric Sector Data Systematization website. Data pre-processing. All values equal to or less than 0 were identified, as well as null data or empty cells. The correlation between the variables, both quantitative and qualitative, that make up the data set. The Python programming language was used with the Pandas library. Data frame construction. There is a total of 19,344 samples and 8 characteristics, which cover aspects such as year, month, group, canton, parish, clients, consumption, and billing. Table 1 shows an observation of the data frame. Preparing and cleaning data for analysis. Records with values less than or equal to 0 in the customer's consumption and billing columns were purged. This operation resulted in the deletion of 7 rows that contained values less than or equal to 0 in consumption, as well as 25 rows in billing. To the categorical variables, the numerical labeling technique was applied in the columns: month 1 to 12, group 1 to 4, canton 1 to 10, and parish 1 to 55, in order to achieve the necessary standardization. After running the debugging, a new set of 19,312 observations and 8 different features was obtained. The data was segmented into 4 consumption categories: residential, group 1, commercial, group 2, industrial, group 3, and others, group 4. The data distribute as follows: Group 1 with 5,684 observations, which represents 45% of the province's total consumption. Group 2 with 5,184 observations, equivalent to 18.5% of the province's consumption. Group 3 with 3,074 observations, which constitutes 28.4% of the total. Group 4 with 5,370 observations, representing 8.1%, as seen in the graph. Separation of variables and evaluation of correlation. Electricity consumption is chosen as the target variable, and location, time, and billing characteristics are chosen as predictor variables. The figure shows a quantitative correlation map between each variable and the dependent variable, consumption. It indicates that there is a strong correlation between the billing characteristic and a moderate correlation with the customer's variable. Canton and parish characteristics represent geographic information. These elements influence electricity consumption patterns, since some parishes may have a higher concentration of customers due to population density and the type of economic activity. Models, training and evaluation. For the residential and commercial groups, data from January 1, 2015 to April 30, 2022 was selected as the training period, while data between May 1, 2022 and April 30, 2023 as the test training period. For the industrial and other groups, data from January 1, 2015 to June 30, 2022 was chosen for training, and data from July 1, 2022 and December 31, 2022 was chosen as the test training period. These divisions were applied to both models. Random forest model. During this process, using the scikit-learn library and the random forest regressor class, using hyperparameters are tuned, such as the number of estimators, the maximum depth of the tree, and the minimum number of samples that must be on a leaf. Additionally, to improve the reproducibility of the results and ensure a more stable tuning of the algorithm, The random state parameter is set to 42. A repeated training process was carried out in group 1, 2, 3, and 4 with the objective of minimizing the MAPE and RMSE. Since random forest does not adapt directly to a time series model, a transformation is used using the min-max scaler in the range of -1 to +1, improving its performance. Happy parameters such as the number of estimators from 50 to 500, the maximum depth 50 to 100, and the minimum number of samples from 1 to 5 are tuned taking into account the particularities of the data. After repetitive evaluations, metrics such as MAPE and RMSE are recorded to select the best performing model. In groups 1 and 2, with 100 estimators, it is evident that the best performance is achieved with the roots in the MAPE and RMSE. In group 3, minimization is achieved with 50 estimators. In group 4, superior performance is obtained with 3 of 300 estimators. In all these cases, a maximum depth of 100 and a minimum number of samples is equal to 1 is used. XGBoost model. It is started with the XGB regressor class. During this process, key hyperparameters are tuned, such as the number of estimators, the maximum depth of the tree, the learning rate, and the random state parameter is set to 42. The training process was run several times for all consumption groups with the purpose of identifying the XGBoost model that achieves the lowest MAPE and RMSE. To improve its performance, a transformation is applied using the scaler, the min-max scaler, in a range from 0 to +1. Upper and lower bounds for the 3 estimator range from 50 to 500, maximum depth in 50 and 100, learning rate in a range from 0.1 to 0.3. In groups 1, 2, 3, and 4, it was observed that the most effective configuration is achieved with 50 estimators, a maximum depth of 100, and a learning rate of 0.3. The figure presents a graphical comparison between actual values and predictions of energy consumption. And discussions. Forecast results. Once training and evaluation was completed, using both machine learning techniques, joint validation was carried out using metrics such as coefficient and determination, R-squared, root mean square error, RMSE, and percentage error, mean absolute, MAPE, that allowed us to determine the most appropriate model to accurately predict electricity consumption. Table 2 represents a comparison of the R-squared, RMSE, and MAPE results between the random forest and XGBoost models, using the test data corresponding to the period from May 2022 and April 2023, which is the prediction horizon. In groups 1, 2, 3, and 4, it was observed that the XGBoost model obtained the lowest MAPE value, but when evaluating the RMSE, it was found that the random forest showed a better fit for these groups. Figures A show the performance of the random forest and XGBoost models through the comparison between real consumption and the generated predictions in order to facilitate the evaluation and search for the optimal model to forecast the electricity consumption. The metrics allows us to identify differences in the predictive capacity of the models, which are observed in the prediction errors illustrated in figures B. In 10, two metrics are shown: the total absolute error and the total percentage error between the actual load values and the predictions. When analyzing the sum of absolute errors, the random forest model scores higher, while the performance of the XGBoost model was lower in comparison. Regarding the percentage errors, it is observed that the XGBoost model exhibits superior performance, followed by the random forest model. When we evaluate the mean squared error, random forest achieves a better fit compared to XGBoost. This is clearly reflected in figures A, where greater coherence is seen between the trend lines and consumption predictions and actual values. This phenomenon is due to the fact that the RMSE evaluates the error in absolute terms in the predictions of electricity consumption. Consequently, the optimal model to predict electricity consumption in the province of Chimborazo is random forests. The result indicated that the mean absolute percent error, MAPE, varied according to consumption groups, being lowest in the residential group, 5.52%, and highest in the industrial group, 13.32%. These findings highlight the effectiveness of random forest in prediction energy consumption, which has important implications for energy management in the province of Chimborazo and contributes to a more efficient and sustainable future. Both algorithms proved to be effective, but random forest stood out by showing exceptional performance across all customer groups, especially when evaluating accuracy with the root mean square error metric.